So, see, things that we see in the world are either measurable or not measurable. Right? Your affection for your dog is not strictly measurable. Your emotions are not measurable. Right? Your appreciation of a sunset is not measurable. But there are things that are measurable. For example, uh, you get in the morning before you get into the shower, you stand on the scale and you hope the number is less than yesterday. That's a measurable quantity. Right? And so, a measurement of that which is measurable leads to datum. A collection of datum, the plural of datum is data or data set. We end up with it. Why is that important? Why do we care? Because science, its strict definition is it is a quantitative, it is a study of quantitative or quantitative study. Right? You ask a question, you may ask a question that uh, if I put more water to a plant every day, will it grow faster? Right? That is a scientific question. To answer that question, you would do something. You would go water the plant a bit more, different amounts of watering. You will take 10 pots of a plant. In each pot, you'll put different amounts of water, and day by day, you will create a table of pot A, day 3, this is the height. Now you're creating measurements. You're creating data. The act of measuring yields data. That's a data set. And that will yield what? It will help you establish whether the hypothesis, any hypothesis you make, is true or not. Whether watering more leads to taller plants. Right? So that is it. And when you look at it through that lens, you would realize that data science encompasses all of science. You cannot have science without measurement, without data. And so it then begs the question, why this new science called data science? Right? How is it distinguished from, let's say, physics or chemistry or biology and so forth? A way to say that would be it is the experimental core of the sciences. When you say that I have a, let's take anything, for fluids, I have the Bernoulli's equation. It's a hypothesis. It's a relationship between the observables. But to validate that hypothesis, you would have to take measurements. You would have to now look for relationship amongst the measurements, validate whether your hypothesis is true or not. And so data science forms the experimental core of all the sciences at heart, isn't it? It is the vehicle through which you validate or invalidate the different hypotheses in the various sciences. So that is data science. Now, while that's a high level picture of what it is, what does it encompass? I could go on and describe many aspects to it, but the best way to say it is with a journey that over the years has matured to be the what you would call the data science journey. When you encounter data, any data, you let's say that you have weather data of a place. You don't know anything about that place. Suppose I've erased the geographical. I don't tell you that is the data for San Francisco. It tells about the weather, the temperature, the pressure, the humidity, the precipitation, the wind speed, hour by hour, day by day of San Francisco. Not knowing anything about San Francisco, by observing the weather, by observing the weather data, the question is, would you be able to get a texture, a very good sense of what the weather is in the city? How would you do that? We'll take that as an example. How would you do that? You have no idea which city it is. With data, the core parts of the journey come right here. You would look at the data, you would see what are the features that I mentioned. There's temperature by the hour, there's atmospheric pressure by the hour, precipitation, wind speed, humidity, dew point, sunrise, sunset times, etc., etc. Right away, as you look at the data, you would say, you would ask natural questions. What's the range of temperature here? So, what's the min max in the temperature? What is the average temperature or the median temperature in this place? These two are different things. To do so, what are you doing? You're taking one factor and you're deriving a number from it that speaks to that set of values. You may have a long table with 1,000 temperature values for San Francisco. But when you say average temperature of the place says something, let's say the average temperature in San Francisco is about 60 degrees. What does it say to you? You probably are not in Antarctica, isn't it? Likewise, it says that you're probably not in the Sahara Desert either, isn't it? Or in Singapore. You're in a fairly temperate region. The fact that the min-max are not too separated, you don't see extremes of temperature. You don't see 110 degrees. And you don't see minus 20 degrees, right? Or 100 degrees or minus 20 degrees. But the temperature has a much narrower band. The variance is low. It speaks to it being a rather temperate climate, isn't it? Just by observing it, you could say, well, it seems to be a bit of a Mediterranean climate. Are we together? Likewise, you can look at the precipitation and you would conclude that this is not one of the rainiest places, but it's also not a desert. Right? So that thing, that sense of data is called exploratory data analysis. And I will posit this as the first thing you do, exploratory. Exploratory data, EDA. It is most important to do this first. Whenever you encounter data, the data will come with many, many facets. The first step that we did very instinctively is to take the data and extract some sort of statistic out of it, various statistics out of it that describe the data, isn't it? What's the min max of temperature? What's the min max of precipitation on a day? How does the rainiest day look like? Right? This is called descriptive statistics. Descriptive statistics can be univariate within it. Univariate means one factor at a time, temperature, pressure, and so forth. Are we making sense? Right? Or it could be multivariate. So for example, one could ask that does precipitation relate to temperature in this place? Is there a correlation? Does that make sense? Right. And you might find that not at the level of an hour, but at the level of a, say, week, there might be some relationship somewhere, right? You might, for example, know that quite often, well, not precipitation, but certainly humidity. The moment in San Francisco temperature goes up, what's the first thing that happens? Anybody remembers? Fog comes in, right? And so it fogs out and it cools down almost immediately. You see beautiful fog. That's what makes your Napa Valley possible, the grapes of Napa Valley possible. Right? So it is an interesting thing you observe because it doesn't always happen. In Sahara Desert, if the temperature goes up, it doesn't automatically invite humidity, isn't it? And that is important, actually. Right? In other places, for example, upstate New York, you see an interesting phenomenon. When the temperature is very, very low, there's no humidity. When the temperature begins to rise a little bit, suddenly you have snow and there's moisture, humidity goes up. It rises up even more, it begins to rain. And finally, it goes up even more, and there is no rainfall. You have the summer season, the spring and the summer season. Right? So every place has a different bivariate or multivariate uh, relationship or statistic. Right? Am I making sense? So you can look for correlation between things. So that is the descriptive statistic. But then beyond descriptive statistic, there is data visualization. What is the data trying to tell you? Now, I would like to pause here because I feel that in modern day, people are so enamored with machine learning algorithms that they give scant attention to exploratory data analysis and to data visualization and also to data manipulation and cleansing. Now, here is the best way to do that. See, guys, why do we do this? These three things, one by one. I give the example of dating. Right? See, in many cultures, especially in the Western Hemisphere, there is a custom that young people, and nowadays not so young people, date. Right? So that's how they find their life partners. So when you go out on a date, let's say, imagine for a moment that you're young and you have taken a person out on a date. You don't know much about the person, the first date, right? Some friend has introduced the two of you, or you met somewhere, maybe uh, in the park or something. You go out on a date. Both of you, and certainly it's a custom here in the Western Hemisphere, both of you will be at your very best, right? The boy will be well shaved, wearing clean shirt. Gone are the dirty t-shirts. Right? The girl will be all pretty with perhaps a bit of perfume, right? And the boy will have some cologne, and the shoes will be nice, and everything will look nice. They are at their very best. But as they talk, and there's politeness, and there is fun, and they do fun activities, they go hiking, all the things that are in quotes safe, that are very likely to create positive impression on both sides. Do you think you really know the person? Or does it take many, many dates, many, many interactions before you begin to get a sense of the person? People who have studied, psychologists, sociologists, they have actually quantified it. I think the number someone told me was you begin to know about somebody much better, and they begin to tell you their secrets only by the time you reach the 50th interaction, give or take. Right? That's when people feel safe and they tell you who they are. Believe it or not. The reason I bring that up because it has a very close relationship to exploratory data analysis. If you go to data with disdain and act as a know-it-all, sure that you know what the data is about, you will get a very cursory sense. It's your first date with data. Data is not going to reveal its secrets. You need to mull over the data, have many dates with data, right? Develop a respect, genuine respect for it, understand its texture, its behavior, before it begins to reveal its secrets. I don't mean it metaphorically, it's very genuine. See, data comes because behind data is a generative force. It could be a force of nature, of physics, of biology, of chemistry, of finance, of commerce. They are generative forces. Data is only interesting because the subtext of your inquiry is you're trying to understand that generative force. Would you agree? You're beginning to get a sense what is the mischief maker like? What really happened? You're like Sherlock Holmes. A crime has been committed. Evidence is the data. You need to figure out who did it and how, right? That's the approach that you should have with data. That behind it is a generative force, a dynamic that the only reason you would approach data and want to study it, to build machine learning models over it, AI models over it, is because you're trying to model the underlying dynamic, which is not accessible to you. Your job is to infer that dynamic. And that is the journey of data science. And it begins, above all things, it begins with a date with data. You need to spend time, do univariate statistics. You need to do bivariate statistics. Then you need to visualize the data. Data visualization is something that I feel in this fast moving world where everything is about uh, generative AI, we tend to underemphasize the value of data visualization. One must lament the poor use of visualization in corporate America or corporate engineering. Most slide decks that have data visualization tend to have the following pathologies. First of all, they will have lots of pie charts and bar charts predominantly, maybe a line graph here or there, and it more or less stops there, or a scatter plot. Is it looking familiar, guys? Right? Most of the time, those, because it's a slide deck for presentation, it will contain embellishments. The pie will have color gradients to it to make it look pretty. It will have a flourish. It will have 3D. How many of you are guilty of creating 3D pie charts with gradients to make it pretty for that? Management expects it. Okay. So I'm going to say, let us let us move past this debauchery of bad visualizations and look at the field of visualizations better. And I would like to, and we will do this, Jupyter Notebooks, we'll see the code. I would like to bring out the value of data visualization with two facts. One a story and one a fact. When you look at data and you're trying to make sense of it, how many of you look at spreadsheets of data and immediately go, aha, I know it. Everything that it says it's told its story to me. It doesn't do that. Descriptive statistics is our analytical tool with which microscope with which we probe it. We get this texture of the data when we know the mean, the median, the min max. They all tell something about the data, isn't it? The variance, the skew, the kurtosis. They tell us something about the data, but they tell one aspect of the data, right? And we are still left with the sense that this data has more to tell us that we haven't grasped. But when we see a good data visualization, its impact on us is immediate. The world's most powerful intelligence engine is not our reasoning ability, despite popular belief. It is as simple as this. It's our capacity to see. See, imagine that you're hiking, as I do, and out of the bushes walks out a mountain lion. Right? Well, with me, it doesn't happen like that. It will just be basking in the sun, and I will come near it and suddenly realize, oops, what's that sitting there? Right? Do you think that my mind reasons like this? Oh, I see a tail. Oh, it looks big. It has 4 legs. The face looks like that of a mountain lion. Let me think what it could be. Oh, yes, it must be a mountain lion. It cannot be a snake. It cannot be a horse. It must be a mountain lion, most probably. Or do you, in the blink of an eye, you look at it and you say, mountain lion, isn't it? We underappreciate that. See, our capacity to reason and conclude is of much recent vintage. Perhaps in the last 100,000 years, we learned to reason. The Homo sapiens learned to reason. Right? to some degree. And the flaw in this part of our mental apparatus is evident. It hasn't gone through enough training, which is one reason throughout your school years, you always hate subjects that make you reason, like math, like physics. How many of you will fess up to that? Right? On the other hand, we like drawing or painting, etc., comes, it doesn't induce stress in you. Now, but what about pattern recognition? Just looking at it. If you see a tiger, it takes you the blink of an eye to know it's a tiger. Right? All the components come together and your mind lights up and says, tiger. Right? When did we develop that ability? That is a remarkable part of machine, what you would call machine intelligence. Whether machines do it, biological systems do it. It is so instinctive and so perfected a form of intelligence that we fail to recognize that it's an act of intelligence to recognize in the blink of an eye that you're looking at a tiger. Right? When did we develop that? If you think about it, little fishes in the ocean had eyes. Amphibians had eyes, reptiles had eyes, all mammals have eyes. Most mammals, to my knowledge, have eyes. Isn't it? So it is of apparatus of intelligence in the biological systems that has had no less than 100 million years of evolution. Would you agree? So doesn't it make sense that if we could visualize the data, our mind would be much more capable of instantly grasping a lot about it, and therefore the value of data visualization. Do not treat data visualization as eye candy. People do that. They say there are mathematicians who actually don't like data visualizations or geometry and so forth. So there's a very interesting tradition. Many statisticians used to say that to compute the statistics in data, descriptive statistics, etc., is all that you need to understand the data. You don't need to visualize the data. And I'll show you a counter example in a few moments. I'll bring up something. It's a very classic example, and you'll see. But before I do that, I would like to tell you a story. This story is about a lady who single-handedly founded two entire fields of human knowledge and human endeavor. Can you guess who am I talking about? Well, not you. So there was a young British girl, the story goes, Florence Nightingale. Almost all of you have heard of her. She felt a calling to do something. So during the Crimean War, Crimea seems to be a bone of contention between the West and Russia forever. Even now there's a war going, as you can see. So during the Crimean War in 1851, she went and started a camp to help the soldiers. Given her large heart and humanity, she would be pretty indiscriminate, couldn't care less whether the soldier was on the Western side, British and French, or was Russian. She would take them all, and she pitched her tent squarely right there, her hospital, right there in the middle of the battlefield, right there, next to it. And so she started taking care of people. And as she did that, she was deeply troubled by the fact that so many people were dying. But remarkably, what she observed, she was a person who since childhood used to carry a diary and make a note of numbers. What happened? How many of this? How many people died from battle wounds? How many died from this or that reason? And what she did is she started noticing something quite remarkable in the data. Paradoxically, she observed that most people who die in battlefields, the least likely cause of death is the battle wound itself. Rarely do people die from battle wounds, from bullets or knives or something. They don't. Most people die from other causes. So, what could those other causes be? I leave that for you to infer. But what she did is she represented that in a chart because, when you show it to, as you know, when you talk to upper management, the visualizations speak louder. She created a visualization of the data and she took it to, I believe, Queen Elizabeth of London, of England. You have to see the visualization. It had such a dramatic impact, such a convincing impact. And the point that she made was so stark that there was no debate about it. The Queen Elizabeth gave her the funding needed to open what you would call today a modern hospital. In those days, there used to be physicians, but to take care of patients, there used to be very few. Like usually, you would harness the prisoners from the prison or the beggars, right? Or servants. She founded the practice of modern medicine. She founded the field of nursing. And the big discovery that she made is that it is lack of hygiene that kills people when they are sick, far more than the actual sickness. And therefore, you must have noticed that in every hospital in the world today, nurses are extraordinarily clean. And hygiene and cleanliness is highly emphasized in hospitals. But that is the power of data visualization. With one visualization, the famous two roses that you'll see, she managed to found two fields. She founded the field of data visualization and she founded the field of nursing, modern nursing, and thus the power of data visualization. I'll move beyond that to data manipulation. Data comes with errors. It needs to be cleansed. See, suppose you were taking the temperature of San Francisco and some equipment fails. A failed equipment might be registering 0 degree Fahrenheit, when you very well know that San Francisco doesn't have 0 degree Fahrenheit, isn't it? Or I don't know when was the last time it did have. I doubt it, right? So data always has errors. They need to be cleaned out. Those outliers, those things have to be fixed in the data. It may have systemic bias. Somebody might tell you that, see, this equipment always measures temperature 3 degrees higher, right? You need to correct for the bias and things like that. That speaks to data cleansing. Then comes data manipulation, right? Data manipulation. What if half the values are in centigrade and half the values are in Fahrenheit? A very simple data normalization is needed, isn't it? Make sense? Other kinds of data manipulation. Think about this. You're measuring temperature in Fahrenheit or centigrade, but you're measuring, let's say you're looking at the temperature of elephants in a zoo. Fahrenheit and centigrade look sensible. But in your whimsical mood, you start measuring the weight of elephants in grams. Right? What would happen? You would have a wide variance of numbers, right? Baby elephants would be, what is it? Let's say 1,000,000 grams, right? And fully grown elephants would be, let's say, 5 million grams. I don't know. 5 ton, 1 ton, does it seem reasonable? Perhaps, right? I don't know how much elephants weigh, but pretty wide variance. So what would you like to do? You would like to normalize the data. You don't want to have one factor with a much narrower range of values and another with a vast range of values. Am I making sense, guys? Right? To normalize that is data normalization of the data, so that one of the easiest thing you can do is make it scale invariant. It shouldn't matter what your favorite scale is, whether you measure it in inches, grams, pounds, like, measure height in inches or centimeters, whether you measure weight in grams, pounds, kilograms, tons, shouldn't matter. What's the easiest way to do that? As you learned in elementary statistics in school, one way to do that is to z-value it, remember? Z-value is, and we'll talk a little bit about that. And today, I won't get the sense to do that. Take the number, subtract the mean from it, and divide it by the standard deviation. Right? So let us say that this is in grams. Mean will also be in grams, and standard deviation will also be in grams. So grams and grams cancel out. Right? What you get? You get dimension unit independence. Right? So it doesn't matter if you started out in tons, measuring in tons, or measuring in grams, or whether you use the imperial system or you use the standard units. So this too is data normalization and part of data manipulation. So these are the three things that you must do with data. Then you may have an hypothesis. Then comes the data modeling. You may have a hypothesis, for example, right? Data modeling comes under machine learning model or let me just say machine learning. When you want to do machine learning itself, when you're dealing with data, comes in two forms. You say that you can make just recognize patterns in the data, pattern recognition. And you may be doing predictive modeling. Are we together? What do we mean by pattern recognition? See, pattern recognition is easier. Suppose I give to you the weight and size of cows and ducks, right? But I don't tell you, I give you a data set. I don't tell you that this is the weight, this is the data for a cow, this is the data for a duck. I take that fact away. Just bear with me for a moment. So let's try to see how the data would look. Would you agree? What would be a good color for ducks? Okay, let's say if your axes are weight and size, would you agree that ducks are small, feathery little creatures? They would be here, and cows are big, heavy creatures. Would this be true, guys? Right. Look at this data. If I remove the axis, there's axes are there, and I remove this fact that it is a cow or a duck, you need not know that. Just without that information, what is it that you can tell about this data? That data naturally bifurcates into two distinct subsets. Isn't it, guys? There's a very natural bifurcation here. What do you call this? They're clustered into two regions of the feature space, the weight and size space. There are two distinct clusters there. To discover these clusters, the human eye just sees it in the blink of an eye. Just like that, you just see it, isn't it? Now the question comes, does data always come with clusters? Let me say, well, you just conjured up a special situation. What if they are horses? So let's throw in some horses also. Maybe horses are not so big. They are somewhat like that. And maybe occasionally in weight and size, you might get mixed up between this. So you might have a little bit of an overlapping set. Horses. But you would still agree that there are clusters in the data, isn't it? Guys, am I making sense? Cow, duck. This data is speaking loudly that we are, what's that? Oh, sorry, cow. That is true. Let's not insult the cows and make them light. Yeah. Ducks, cows. Right. So now that's the value. To see, 1 second, I'll take this. Just to see clusters in data, do you think you learn something about the data? Right? You learn something about the data. Another illustration is, I'll take questions. Another illustration is, suppose you get lost in San Francisco and you don't know, I forget the world, nowadays everybody carries this news and cell phones and Google Maps. So instead of people looking up, there was a Plato statement, man is the only species that looks up. Now, it turns out on Earth, there is no single species because man is always looking like this at the cell phone. right? Even walking. But anyway, jokes aside, if you land in San Francisco, let's say you land in the financial district and you're lost, you're trying to figure your way, let's say to the Golden Gate Park, right? Without knowing the maps, you would be sort of doing things by trial and error, isn't it? You would just move there. It is pretty much exploration. Go in some direction. After a little while, think, no, 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 this is not helping. Let me try another direction. And you zigzag your way, and you'll eventually land near the Golden Gate Park. On the other hand, suppose you have been in a hot air balloon, right? And you are over the city of San Francisco. What happens immediately? You notice the financial district, right? Is at the tip of the peninsula. You notice uh, where the Golden Gate Park is in between the green patch. You see the residential areas, isn't it? And common sense tells you that if you want to go to the Golden Gate Park, it might help to go, let's say, southwest. Right? Your best bet could be just making a straight path southwest, and you'll probably hit upon the Golden Gate Park. Am I making sense? So what happened? Pattern recognition and even knowing the clusters helps you. You know that all the financials are clustered at the tip of the peninsula. All the trees are clustered in the Golden Gate Park. All the residentials are south of that, right? More or less. So that gives you, that learning helps you navigate. So now you may say, do we genuinely have clusters all around us in the world? How many data sets actually have clusters? The world comes with variety of data sets: financial data, time series data, uh, atmospheric data, space data, biological data, medical data, chemical data, right? Human behavioral data, crime data. Right? Of all the infinite varieties in which data sets present themselves, what proportion, if you had to guess, do exhibit clusters? Would somebody like to take a guess? And then I'll take your question. Just make a guess. I think some of you have. Why? When I look at this, I'm looking at the air in this room. All the molecules are buzzing around. Do you think they form clusters? They don't. No, no, no. You're talking about classification. I'm saying generally, how often do you expect to see data as clusters? So that is an example where it is there you do see clusters. Go ahead. Oh, jaundice ties. If you look for clusters, you'll see clusters. That's an interesting perspective. That's right. Okay, let me take your question. You have been waiting with your question. Okay. So there's a very interesting thing. Nature or data will most of the time, almost always, show some degree of clustering. In fact, an absence of cluster, a uniform spread of data, random spread of data, is the exception rather than the rule. And when you see that, there is actually an underlying reason why it is so. So your basic instinct should be that there are clusters in data. I'll give you an illustration of this. See, have you noticed that when you get, well, there was a time I used to teach this 20 years ago, and I used to use the word letters. But letters, I don't think anybody gets those anymore. Emails, but even those are getting archaic. So the sum total of all the messages that you're receiving by instant messages and what are the other things, WhatsApp and so on and so forth, email, everything put together. Have you noticed that some days you get a deluge of them? Other days you get a nagging feeling that you're being ghosted. Anybody resonates with that? Right? You see that it doesn't come at a steady rate. Now each of these is coming from a different person, different human being. And suddenly it seems that everybody has collectively decided to remember you. And on other days, they have all collectively decided to ghost you. Why is that so? Likewise, if you stand on the bridge of a overpass of a highway, bridge over a highway, you will observe that even when there is no traffic congestion, if you carefully watch the cars flowing by, you will observe this. You would expect all the cars to be spread out uniformly or near uniformly, right? Randomly on the highway. But what happens is that one bunch of cars come by in wave, it goes by, there is a gap, and then another bunch of cars come by. Has anybody observed that standing on an overpass? Right? They are clustered, they are bunched. Not on a highway that is stretching for 10, 20, 30, 40 miles of open highway. Yes, completely open stretch of highways, you'll still see bunching. You'll still see clustering. Oh, they form bunches, they form clusters. So clusters are actually everywhere. And the reason is subtle. It has to do with physics. Most dynamics, most causative factors in nature are nonlinear factors. There's nonlinearity there. Generally, without people realizing it, most of all that happens in nature and actually in other data, financial markets, etc. It is what you find is neither perfect order nor complete random absence of order, namely randomness. Right? See, there are two things. Things can have perfect order, very ordered, right? For example, let us say that you got a box of numbers, right? Or you threw a dices, and first it was one, then it was two, then it was three, then it was four. In a perfect sequence, it comes out, right? Or sometimes there is no order at all. Like for example, the molecules are buzzing around. You would imagine that their velocity vectors are in random directions. It does happen, but generally, nature chooses to inhabit a region in between pure order and pure disorder. In fact, it inhabits a very interesting region where whenever there's nonlinearity, that is called the region of chaos. Right? Now, chaos doesn't mean what it means in popular imagination, randomness. Chaos actually means hidden order. Order is there, but it's latent, it's hidden, invisible. Whenever you have nonlinear systems in chaos, you'll almost always see clustering. That's the deeper explanation of why you always see clusters in the world. Right? It's very subtle actually. Why you see that all over the place. So so that speaks to the existence of clusters, and we will use machines to find clusters. One of the goals of data science is to find clusters. There is another pattern recognition that's quite popular, that is of dimensionality reduction. So we talked about clustering. Clustering. The other is dimensionality reduction. You don't. You do have a noisy separation. In other words, you can find only the optimal separation, but there will be some horses that you got wrong. Right? Some horses will be here, and some cows will be on this side. So you'll never get perfect separation between the cows and the horses. That is a very good point. Actually, thank you for asking this question. How do we say it is not one cluster but two clusters? Actually, and nice that you asked that question because it gives a very interesting problem. What is a cluster? See, and it is scale dependent. From a far off distance, it is perfectly legit to say that this whole thing is one cluster. And that cluster, if you zoom in, contains two subclusters. Right? And actually, that answers a nagging question. If clusters are so dead obvious to the human eye, why isn't there an algorithm taught in elementary um, computer science, like as in first, second year computer science courses? We can do searching, we can do sorting deterministically, isn't it? We have all sorts of bubble sort and whatnot. Why can't we cluster? And part of the reason, the reason that you can't cluster, it's an NP hard problem. is because clustering is also scale dependent. There are clusters within clusters within clusters. Right? And ultimately, you have to choose the scale. Now, today, I'll give you some texture of it with real examples. When we do the labs, all of this will become real. Right? But your point stands. It's a good point.
When you say scale for clustering, is it like you defining on your perspective what is a cluster? When we
Yes. So,
say
from your
10,000,
perspective, exactly, exactly. So, I'll give you an illustration. See, when you look at a galaxy in the
mhm,
sky, when you look at the night sky and you see a galaxy, to you, that galaxy is a cluster of stars.
correct,
But if you zoom into that galaxy, you might see further subclusters. You zoom in more, you see a planetary system like our solar system. That itself is a cluster, zoomed
correct.
in, right? So clustering is always scale defined at a level of scale.
Yeah, thank
Distance.
you.
Oh, I didn't realize lots of people have joined over Zoom. How many? Oh boy, we do have quite an audience here. All right. So do please feel free to ask questions. Now, we'll talk about dimensionality reduction. Let me explain that in two ways. Let us say that you are looking at, let's say you're looking at medical data, right? And no, not, let's take something simpler. Let's say that I put in the middle of this room, or imagine, not even middle, imagine that you're gone hiking and you're camping. What do we all do around camp when we are camping? The first thing we do is we wait for the sunset and promptly put up a campfire. We do that, right? The moment you put up a campfire, then you sit around it and tell stories. Now, imagine that you're looking at the temperature at a certain distance from the campfire. It's an observable. Now, distance, because the ambient space is three-dimensional, XYZ, isn't it? You can put a coordinate system, maybe center it, originate at the fire itself, and look at the location. At every location, you can observe the ambient heat that's coming, right? Now, you have data now. That data will have these variables. It will have X, Y, Z, and let's say amount of heat that your equipment is receiving, right? Pointed towards the fire. Let me just say heat. Right? Does that make sense, guys? Right. You could measure it. This data is what? It's four-dimensional data. But suppose, or you can think of it as heat, or you can think of it also as luminosity, how well lit it is. A coordinate system, imagine that you put up coordinate system at the fire, right? So wherever you are, that location is, guys, are we making sense? This is just the location. Location is given by that. We inhabit 3D space, no? Yeah. So far, so good. Now, after a little while, you'll realize that maybe what we really need is just a radial distance heat, incident heat, whatever the incident heat is, incident heat. Would you agree that you could actually reduce XYZ to only one variable? What could that variable be? Distance from the fire, isn't it? Just a distance. Direction doesn't matter, right? How far you are from the fire says it all to the first approximation, isn't it? So, what have you done? You have reduced the dimensionality of the data. You have created a new variable R that is just as expressive. You can write the heat equation, heat, as a function of R, not an heat as another function of X, Y, Z. Instead of writing it like that, you could, these two are equivalent representation. But when you reduce it like this, and you realize that heat is just a function of R, do you think you have developed some understanding into the data, some insight into the nature, the how heat behaves? Isn't it? So dimensionality reduction gives you insights. Right? That is the value of dimensionality reduction. It's a form of pattern recognition. You realize a pattern in the data. Angles don't matter. Only distance from fire matters, or distance from a candlelight matters for light. Now, there is another way to look at dimensionality reduction. Suppose you are making a model or you're looking at people's diabetes. These days, circa 2026, the gold standard for measuring a very scalar value to measure how much diabetes you have is a 3-month average of hemoglobin A1C, which gives you an averaged amount of sugar floating around in your bloodstream. Right? It's a medical observation. Do we know what hemoglobin A1C is? Think of it as a measure for diabetes. If you go to a physician, they'll measure it for you. Now, you might suspect that diabetes is caused by many things. You might believe that your diabetes may improve if you wear blue shirt. Now you know why I wear it. No, I'm kidding. Or you may feel that black shoes help you more. Color of shoes matter, color of shirts matter. Maybe your, and you may have other factors, like for example, how much exercise you do on a daily basis. What's your total caloric intake? How much sleep you get? What is the level of stress that you internalize every day or you live with, ambient stress? Right? Now, and while you're at it, you might also decide that the amount of market going up or down, right, is affecting your diabetes. But now you would agree that not all factors are equally relevant, isn't it? You might be disappointed to learn that the color of your shirt and of your shoes don't quite matter so much. Right? That the affective factors for diabetes are actually other factors. They are the lifestyle factors like the amount of exercise, your age, right? Type 2 diabetes, your age, how old you are, the caloric intake, the ambient stress in your life. Right? Think of it as average stress that you carry forward in your life, that you internalize. Right? So just to make it very simple, who carries more stress, a Wall Street trader or let us say the ice cream shop, the ice cream salesperson on a beach, day trader. Right? So that's has higher stress level. So from that perspective, right, you could quantify that. Right? Yes, that's right. So what happens is to build a model of diabetes or A1C, which is the target variable, you are saying that A1C, Y, A1C is function of, initially you started out by saying function of weight, right, of calorie, age, exercise, caloric intake, exercise, stress, shirt color, shoe color. You might be modeling with all of these factors, but then you realize that some easy stuffs don't work. You might come to the conclusion that Y is actually another function in which these two are not there. Am I making sense? So you have reduced some dimensionalities. That is another form of dimensionality reduction. Yes. No, it is a posteriori. Your analysis shows you shouldn't care about this. Right? So, so the question that was asked for those of you who are remote, sorry, actually we should get the microphones out, desk microphones, is this: do we do dimensionality reduction to bring about computational efficiency? No, not really. To know that changing your shirt color and your shoe color is not going to affect your A1C level is not just a computational efficiency question. It's a question about understanding the nature of diabetes itself. So dimensionality reduction brings its own insights, right? In which case you're dropping of factors which are non-effective or marginally effective, right? In the first case, when you're looking at fire and the temperature, to see that given XYZ, I can create a synthetic a factor called radial distance from fire, which is synthesized out of XYZ by some formula, is also a moment of insight, because that insight says it doesn't depend upon the radial aspect. Fire is isotropic, in other words, isn't it? The heat from the fire radiates isotropically. The light from a candle radiates isotropically. When data shows that to you, that really is that thing, that dimensionality reduction is illuminating, right? And a form of learning, both for human beings and for machines. And therefore, it comes under the umbrella of pattern recognition as machine learning. No, causation is a completely different topic. And why don't we do that? Uh, that was still a part of exploratory data analysis. I sort of jumped over it, but why don't we bring up causation? See, there are a couple of fallacies that, but if we go on like that, are you guys okay if I take in a little bit more time towards the end? Right? So causation, since childhood we are told that cause, correlation is not causation, right? Yet we keep mixing them all the time, right? And the internet is filled with amazing coincidences, right? Completely accidental correlations that have that simply don't make sense in causation, right? For example, the more the scientific papers are published over the years, the more people have committed suicide. Right? Now, right? So yes. Sorry. So no, let's continue. Likewise, they are very accidental or fictitious correlations. But correlation may have causation associated with it. For example, there is a strong correlation between the number of hours you spend in the library studying and, and how well you do academically. So, correlation does not imply causation, but it doesn't negate it either. And sometimes correlation can have, there are many relationships between correlation and causation. So, one of them could be more subtle. For example, some things have underlying causes. One underlying cause, for example, is now, see, if you look at the population, this is a very provocative one. So I must tell you that it may be, you might get provoked by this, but forgive me for mentioning this. The population of donkeys in, let's take some country, maybe Thailand or China, right? Actually, I think it was China. Somebody showed me the data for that. Is correlated with the population of humans in India. Pretty closely correlated for the last almost 30, 40 years. Now, you simply don't want to imply causation, isn't it? That would be absurd. But there can be latent factors. What happened is both India and China were British colonies. As the colonies, that world of colonialism came to an end, both of these countries were left lands of beggars. It's a reality. I've seen that poverty in my childhood. Railway stations in India at least used to be the sleeping ground of 1,000 beggars. The streets, footpaths used to be that. We have risen from the ashes, and the government of both of these countries have, frankly, despite all their defects, have done extraordinarily well in bootstrapping the country from the ashes. Like Phoenix, these countries have risen from the ashes. In a space of just 75 years, it is amazing how much they have come forward. They have increased food, resources, everything in both these countries. When resources increase, Malthus law of population dynamics, what happens? More resources mean more population. Population of everything goes up. Of animals goes up, of humans go up, of birds go up, isn't it? There's just more to eat. So when you look at it like that, is it any surprise that there would necessarily be some sort of a positive correlation between the population of donkeys in, let's say, China or Thailand and people in India? You would expect that, isn't it? In any of the colonies. Right? So sometimes they can be latent causes. You have to know this about correlation. Right? Now, while this correlation and causation, people are always on the guard, right? The moment somebody shows you a correlation diagram, you immediately say, well, that doesn't prove it. There's a famous story, apparently, the big tobacco in US. So I heard this story. And I'm sure that it's been oversimplified, so take it accordingly. The big tobacco kept on saying that smoking does cause no medical harm. And people were observing that there's a relationship between that and lung cancer, right? So they were showing that the more you smoke, the more likely you are to have lung cancer incident. So the evidence was mounting, correlation evidence, and they got sued. So big tobacco began to get into trouble. So they kept denying the correlation. That wasn't working. The correlation was too strong. Now they had to prove, they had to win it in court. So then they had to bring the big guns. What they brought is one of the greatest data scientists or statisticians, right? His name is Fisher from England. So Ronald Fisher was called in. He loved smoking and he believed there's nothing wrong in smoking. So he flew into the court and he was asked, do you think this correlation exists? And to everybody's surprise in court, he says, of course it exists. You can see it. I'm not going to deny that. Right? So now people thought, okay, tobacco is in big trouble now. Big tobacco. So they said, then isn't it given that tobacco causes cancer? He says, not at all. Right? It's the other way around. Cancer causes tobacco smoking, cigarette smoking. How so? Right? He says that, when people have cancer, they don't know, but their body craves a pain relief, the pain that you can't see. And so you start smoking. So, of course, tobacco is the great philanthropist that's alleviating the suffering and pain of the world. Right? So that is the problem with correlation. This is history. But there's another aspect that goes unmentioned. The great statistician Stigler wrote about in his book, he mentioned this, that the sequentiality is actually the greater fallacy. If something happens after something else, people believe that the first must be the cause of the second. Right? I'll give you an example. Every time in any country a new prime minister or a new president comes, right? The moment GDP goes up, he takes the credit, right? And the moment something bad happens, my predecessor was the cause of it, right? It happens in corporate management also, right? The moment a new manager comes in, everything that is right is because of him. Everything that is wrong was because of the predecessor. It's as absurd as that. In other words, simply because X happened after Y, right? Y was not the cause of X. I make it absurd by making this statement. I came to Silicon Valley in the late 90s. Right away, there was a dot-com boom. I must have caused it. It's absurd. That's a sequentiality fallacy that human beings have. So anyway, there are lovely fallacies in data that you find. It is amazing how often we get caught up in this. There is a To give you an example, there is a fallacy that more and more people get into. We are taught in education that don't discourage children, don't beat them up. Instead, give them positive feedback. If they do something well, praise it. Yeah. It's called the principle of positive deviation. You can actually teach children and make them really good with just positive feedback, and human beings also. Workplaces, managers learn the hard way that positive feedback is all you need. Right? So, one group decided that that's not true. I think one coach in one soccer, some team, I think football team or something, did the opposite. The moment somebody would do badly, actually, no, there are two incidents. One was with a coach, and one was with the aeroplane pilot coach. What he would do is the people who were learning to fly planes, if they would do badly in the Air Force, he would absolutely rain down on them. Right? And then he observed that the next day they would do better. Right? Same thing was observed by a coach, actually right here at Berkeley, in some, what was it, football or something. Both of them, both these things actually became, they went ahead and wrote articles or paper about it. That actually it helps to give negative feedback. What is wrong with that argument? They have data to prove it. They went and they absolutely rained down on the guy who did badly. Next day, the fellow improved. What's wrong with this argument? Can you identify it? Can you tell why you should not? Data is in front of you. This flight coach absolutely shouted at the person who made a lot of mistakes during flying. Next day, he didn't make so many mistakes. Consistently, he observed it in the data. Likewise, the coach observed that if he shouted at the players, next day they did better. Doesn't it prove that shouting and harsh criticism and scolding is absolutely the right thing to do? How would you disprove that? No, I have data here. How do you disprove it? I just gave you a hint, sequential, related to the sequentiality stuff. See, guys, what you are saying is, how do you know that shouting improved that? You need a control group. You need a group on which you did not shout. And see, you need to take people who did badly, take half of them, shout at them, other half don't shout at them. And actually what you will observe is that they will both do better the next day. The reason is that, see guys, no matter how good you are, someday you have foggy minds. Maybe last evening you had a bit too much to drink. Maybe you didn't sleep enough, right? Maybe you got bad news today, right? Things happen in our lives. So our performances go up and down. So if you have, most of the time you have normal performance. Someday you'll have extraordinary performance. Someday you'll have extraordinarily poor performance. But the very fact that they are outliers, next day you're much more likely to do better anyway, isn't it? And so you should be very careful. Most people begin to mix sequentiality with causation because they forget to have a control group. That's why in medical we have control groups. Right? Anyway, so we'll move forward. Thanks for the digression. We'll move back now to machine learning methodologies. Pattern recognition, we said there's clustering and dimensionality reduction. Go ahead. See, the sample sizes matter. And now we are getting into the mechanics of it. There are ways to quantify confidence intervals and so on and so forth, and error bars. That gets technical. So today is a little bit lightweight, but in the lab, I'll go into some of this. Let's get it to the lab. But I'm almost done. Let me come to the predictive modeling. Predictive modeling, again, the two things that we'll cover today in the lab are two things like this: regression and classification. See, the two narratives that I take for both of these are, imagine there is a young entrepreneur on the beach. She wants to open an ice cream shop. She believes children come to the beach, they'll buy ice cream, and that's her business. Right? She observes that she tries to model how much ice cream to buy from the wholesaler every morning because ice cream is a perishable good. You buy too much, it will go waste. If you buy too little, then you'll just be sitting there twiddling your thumb and telling the children, I'm done, no more ice cream. So, what is the thing that you want to optimize? That you buy just enough ice cream that the children actually will buy, isn't it? Otherwise, it's a tangible loss for you, either way. Right? If you buy too much, the loss comes from unnecessary cost. If the don't buy enough, the loss is in terms of lost revenue. Right? Former is lost capital, latter is lost revenue. Isn't it? Making sense, guys? So it is in her interest to make a very good prediction of how much ice cream today will sell on the beach. The affective factors could be temperature, how windy it is, right? Precipitation, is it raining? Is it a work day or a holiday? Because who brings kids to the beach? Parents. And parents are chained to the employers. Right? Work days, they work. Or to the employments, rather, chained to the employments. Now, that is regression. What are you trying to predict? A number, an amount of ice cream, a measurable, isn't it? So many pounds of ice cream you're trying to estimate, isn't it? When you are estimating a quantity based on certain affective factors, you say you're doing regression. Right? On the other hand, suppose I were to tell you, here is the weight of an animal, here is the size of the animal. Tell me, is it a cow or a duck or a horse? Are we together? Now what are you trying to do? Are you trying to predict an amount? No. You're not trying to say 80% cowness and 20% duckness. Right? What you're trying to say is cow, duck, horse. When you're trying to identify what it is based on certain factors, right? It is an identification task. You call it classification. Now, it so happens that most machines, the way they do that is, they actually, classification sometimes is a hidden form of regression. What you do is you predict the probability, let's take just cows and ducks, probability that it's a cow. Right? So probabilities take values from 0 to 1. That's again a measurable quantity. But you put a threshold there, let's say 50% threshold. And then you say, okay, if more than 50% chance it's a cow, it must be a cow. I'll predict it's a cow. That's one way of putting it. You don't have to put your cutoff threshold at 50%. For example, if you go to the hospital and they often some anomaly in the body, should your physician get worried if there is a 50% chance that you have cancer, or should your physician get alarmed if you have so much as 5% chance of having cancer? Right? 5% is already too bad. Another way of putting it, would you cross the road if you have a 5% chance that you will be hit and die? You wouldn't, isn't it? So, what's that? Come again? 5% chance is okay. All right. Yeah. Go say that to your family that I'll cross the road if there's a 5%, only 5% chance of being hit. No, 5% chance of being hit. I think you take too many chances. Your risk profile is very different. That's right. Most people, like if you ask your family and tell them that, should I cross the road? I have a 5% chance of being hit. They will hold you back. That's the thing. So in other words, where you put the cutoff is situation dependent. But in any case, classification is telling what it is. Is it a cow or a duck? So guys, did we come to the whole scope of, or broadly the scope of data science? It has exploratory data analysis, and it has statistics, descriptive statistics. It includes data manipulation and cleaning. It includes data visualization, and it includes then the machine learning part of it, modeling. Modeling also, you can build a model from data. You can learn from data. That is the machine learning part. But at the end of it, you need to validate whether your model is correct or not, right? That is the evaluation and metrics part of your model, right? Whether you're doing pattern recognition or you're doing predictive modeling, there's a host of metrics that tell how good your model is and are you barking up the wrong tree. Right? So what I would do, so having given you a general idea of this field in this way, what I would like to do is give the next hour and a half to walking you through code and showing it with real examples. Would that be fair, guys? We can take a 10-15 minutes break. Let's get into code and see it for real. Yeah, yeah. No. It's a whole field. So you have to learn the field. All right. The question was, how do you pick the dimensions of it? So there's a mechanics to it. We'll learn into that. So what we are going to do is change gears, and we are going to now look at everything from a very practical perspective. So I talked about the importance of data visualization. And people have many times dismissed data visualization as eye candy. Even serious mathematicians tend to do that. They feel that if you have given a good statistical description of the data, why do you need to visualize it? There's a little bit of a story I like to tell you. One of the most remarkable books that I read, which was called Visual Complex Analysis and so forth by Needham, he talked about a quote from Sir Michael Atiyah, one of the greatest mathematicians of our field. He said that, suppose there is a Faustian bargain with the devil. The devil said, I'll give you a machinery. With this machinery, you can solve any problem. Right? Any problem you want to solve, you can solve with this. But in return, you have to give me your soul. You cannot look at the data geometrically or visualize it or something like that. Right? And apparently, in the view of Michael Atiyah, that is what has happened to the field. Have you noticed that our field of machine learning and AI, it is so filled with symbols. And before you know it, you look at an equation and you say, oh my God, what is this? Right? But actually, most of them have very simple geometric meaning. Now, we won't go into the geometry because that's of the machine learning, but something more mundane, visualization. I find that people don't visualize enough. And then there are people who will say visualization isn't quite necessary. The statistical descriptions are enough. It sort of, I'm extending the point that Michael Atiyah, the great mathematician, makes. So let us bring back visualization. This was best illustrated by this great scientist, statistician, or what you would call today a data scientist, Francis Escombe. What Escombe is, he created 4 data sets. And when you look at this data set, all of these, imagine that Y is the response variable, X is the input variable. You get a bunch of numbers, isn't it? Now, you can stare at the number and try to make some sense of it. But let's see what happens when you do descriptive statistics. Remember, what did I say? You should do descriptive stats. You do descriptive stats between the 4 data sets. What do you observe? They have exactly the same count of data, 11 points. Isn't it, guys? Remember, Escombe created this data by hand before computers. Right? What is the mean? The same. Mean of X is the same. Mean of Y is the same. X and Y. Right? Even the standard deviation is the same. Do you notice how up to the second decimal place, the standard deviation is the same? Minor variation in the 4th, 5th decimal places. The correlations are almost the same. Up to 3 decimal places is the same correlation. Slope is the same. Would you agree? Half. R squared, that is how much a linear model would explain this data is the same, about 2/3 explanatory power. Sum squared errors is also the same, MSE, right? If you want to mean it, you can divide it by n. But here, sum squared error equivalently. Would you agree that this data has to look very, very similar? They probably describe the same dynamic. If you look at the statistical description, you would say, well, they're about the same thing. Would you agree, guys? Any descendants here in the room? Common sense says if it matches so accurately, they must be describing the same generative dynamics. Not necessarily. We have one dissident. Argue for it. Assuming they're the same context. It's just abstract data. Isn't it? Isn't statistics arguing that they are essentially explaining the same dynamic? Isn't it? The same relationship between X and Y. Assume that whatever units you want to throw at it. Now let's see what happens when you visualize the data. Now look at this data. Sorry. Yeah. Oh, here we go. Let's go to let's view it as Jupyter Notebooks, because in this it's not. I want to follow it, or maybe I can follow it here. Importance of data visualization. Okay, guys, now look at this. You look at these 4 data sets. Would you agree that these are vastly different 4 data sets? Notebooks, much easier to see. Yes. Do they now seem to explain the same dynamic? They don't, right? They're quantitatively different, and even just looking at it, they're different data sets. They're about different things. And that is the point of data visualization. Descriptive statistics is not enough. It can mislead you. But forget, instead of doing all sorts of complicated descriptive stats, just one look at the data would tell you that you're talking about completely different dynamics. Would you agree? That is the point to be made. Then there is even more simple, another data set in the same category. Look at this data set, which is made up of 13 data sets. They have some names, forget about the names. They have exactly the same count, same mean of X, mean of Y, standard deviation, correlation. A descriptive statistics, a statistical description would lead you to believe that these data sets are essentially underlying is the same dynamic, isn't it? It can lead you to that belief. But let's look at the data. This is the first data. Oh, what does it look like? Dino, right? Now let's look at what the other data sets look like. Do any one of these 12 data sets look like Dino? They don't. One looks like a star, another looks like a circle, one looks like a donut, one looks like a cross, isn't it? So how much texture? So folks, do I need to emphasize the importance of not skipping data visualization in your data science journey? So hopefully you realize visualization is a necessity. It's not eye candy. Let's move to the famous history of the field, Florence Nightingale. Yes. I'll show you the book. It's with me. Look at visual differential geometry and forms. And another is visual complex analysis. These are great books. People, you can just imagine the hard work it takes to write such textbooks. Anyway, coming back now, Florence Nightingale, Lady of the Lamp. She gathered data on people's mortality from diseases, wounds, and other causes. When you realize that this data set has only 24 rows, 2 years worth of data. Do you see this, guys? From 0 to 23, 2 years worth of data, right? Covering, which are the years it covers? It covers from I'm sorry, I got that wrong. From I said 1851. I should have said 1854. 1854 to 1856 March. It covers 2 years worth of data. Now, and by the way, when you do a data visualization exercise, we just show you how to create effective visualization. So this would be the typical visualization you would do using your basic, I don't know, Excel or whatever, basic tooling, isn't it? Bar chart. Looks impressive. It says something. If you really stare hard at it, it will tell you that, look at that. The death from disease is more than the death from wounds. Right? So the signal is there. But what she did is she converted it into her famous rose diagram. This is what she presented to Queen Elizabeth. Or was it Queen Victoria? I think it was Queen Elizabeth. Look at that. This is the famous 2 roses for the 2 years. And what do you see? The death from actual wounds is so minuscule compared to the death from disease. Do you see that, guys? Right? Doesn't it, in a very visceral way, convey to you how to protect your soldiers? Right? What is the first thing you need to do? What will you do? Give them steel armors for battle, or rather give them better hospitals? This is it. It says that. And now you may say that, see, she did it by hand. This visualization is by hand, and this is a handwriting. Now you may argue that, how do we create such good visualizations? Right? We don't, what are the data visualization tools that people use? For example, if you're used to Python, you would typically use Matplotlib or Plotly or etc. Seaborn is based on Matplotlib, yes. So what these tools, people underestimate the power of those tools. Someone said, you can't make this in Matplotlib. It was a challenge to us. Can you do this in Matplotlib? Matplotlib helps you make your bar charts, etc., etc. Right? That's a general impression. Simple, boring charts. I mean, if you agree with that, default, boring, vanilla charts. So see what we do. That's not true. Yeah, it just shows that no matter which month you look at, in every single month, deaths happen far more by other causes than from this. The sort of value is this. Look at January. When it is very cold, people are not out there aggressively fighting. It's cold. Yeah. Fewer. Yes, it's fewer. But in winter, they're high because flu, cold, all of those things are happening, right? Infection spreads. So there is value there. Now, what we do is we say data visualization is a journey. You start with something simple. Here are the 2 bar charts that you would draw with 1 line of code, guys. Does it make sense? You take this data, if you use Plotly, if you know Matplotlib, it is simply a bar chart. Would you agree? Do you notice that x-axis is date, y-axis are disease, wounds, and other? So you'll get this plot. This 2-liner will give you the plot. The rest of it is just naming the axis. So far, so good, guys? Not hard at all, I hope. Right? This line creates a figure. This line creates 2 plots. It says left and right plot, subplots. 1 year. In the one plot, you say plot. X-axis is date. Y-axis are 3 things. Disease, wound, and others. And then likewise for the other year. Is the code looking simple, guys? So we use this as a starting point, and then we say, let's make it a bit better. Let's turn it into a polar plot. All you have to do is go from XY axis, Cartesian axis, to polar axis. When you do that, and you add a little bit of dash to it, and so this is a journey that we take you through in our data visualization class, and you end up with this. How many of you would agree that this looks This is not what you would have expected to create with Matplotlib unless you know that it is not about the libraries, it is about your ability to use those libraries. Right? So just a few lines of code. I can walk you through this. What we did, we first have the X, then we are saying that we are going to make a polar plot, axis as a bar. We give this disease light gray, black, etc. The rest of it is just patching. Right? Now, when you do polar bar charts, it is literally a polar bar chart. Right? And the rest of it is decoration. And by the way, this is the original. This is a Florence Nightingale's diagram, and this is our diagram. Would you say that this is pretty close? Isn't it? So never ever underestimate the power of most of the modern data visualization tools. With bit of effort, you can actually build any visualization. See, it is called visual storytelling. You can tell the story with a table of data. You can tell it with a bar chart. But human beings respond really strongly. We have a strong response to certain visualizations and not to others. When the message is conveyed in this way, it has a very direct impact, right? Of course, it leads to founding of two fields then. Yeah. This is called the two roses. This is Florence Nightingale's famous two roses. Right? So guys, Matplotlib has things I won't get into. So this is just an invitation for you to learn data visualization. Now, I must talk about the point that I raised about pie charts, and especially with color gradients and 3D. Does the 3D convey any information that a flat 2D pie chart doesn't convey? What? 3D doesn't convey any information. I mean, if you put the depth to mean something, yes, but most of the time in your PowerPoint, the 3D is just for visual eye candy. Right? Now, I'll tell you something interesting, guys. And it's a point made by Professor Tuft, Edward Tuft, who is a very strong voice in the visualization community and a strong influence. He says, use the principle of least ink. Good visualizations are scientific diagrams. Nothing should be unnecessary. The third dimension doesn't convey anything, remove it. Unnecessary color gradient shouldn't convey anything. It's just jarring. You begin to wonder, why is there a color gradient? Isn't it? Don't put it there. Data visualization is not marketing. You just keep it as is so that there is no cognitive overload. Everything should mean something. And he calls it, roughly I would translate it as the principle of least ink. Use the least amount of ink possible. In fact, he goes so far as to say there is no use for pie chart because you can just use a donut chart. You get that, right? Suppose I have a chart like this, pie chart like this. Right? I could actually not keep and fill all of this with color, which is sort of too much visual assault. Suppose I delete the inside of this yellow line, right? And I make it only, and I just give it, then let's say this part is this, and then this part maybe this is this, and just to convey the point. This is called a donut chart. It uses far less ink, but it still conveys the proportions, isn't it? Right. There are many reasons to do that because area grows as square, and so visually something that is big looks bigger than it should. Right. There are other aspects. So people look at many aspects of visualization theory, but if you keep this in mind, that keep your visualization simple. Beauty can be, aesthetics can be achieved without using eye candy. Right? Don't use eye candies. Tuft, Edward Tuft. His great classic books are Amazon. Let's go to Amazon. Um, one of it visual display of quantitative information. You see this book? It started with that 1997, but now he actually gives course on data visualization here at Stanford. It's a very, very good course. People absolutely love it. They feel that it changes their perspective. If you get a chance, read Taft. Strong influencer. All right, coming back to where we were. Where were we? Right. Now, I would like to give you a sense of the distributions. How about this? I just go to normal distribution. Do we know what normal distribution is? A bell curve, right? So what is two characteristic? Width, the width of the bell curve, the spread of it, and where is the center? Mu and sigma. Right? Mu is the center and sigma is the spread, measure of spread. Leaving that, there is something beautiful in data science. It's called the center limit theorem. I'll just mention it as this. It says that no matter what your probability distribution of data is, if you sample, right, if you find anything, like let's say that you're trying to find the mean of that distribution, right, you can take subsamples of the data and you can keep finding the value of that. And what you will find is that all of those things will form a bell curve towards the real mean, because see, you have taken just a small sample of the data, right? So you may say that, bigger the data, then I would know the real mean. The human population, what is the mean height of people? You can't line up 7.5 billion human beings. You will take some sample of people. But how do I trust that you didn't go to the basketball court and pick up some guys and the sample mean now says 6 foot, right? As the average mean height of people. Or you went to kindergartners and came back with the conclusion that the mean height of humans is 3.5 feet. Do you see the problem? Your sample may have intrinsic bias. So what the center limit theorem says that if you take lots and lots of samples, the mean of the mean will be the true mean. Right? The means will be distributed, or whatever statistics you're looking at. Do you notice that the means are, no matter what your distribution is, the means will get distributed. Like, for example, this is a very odd distribution. It's peaking here. Right? This, for example, maybe the salary distribution in your company. Right? So way out here is the CEO earning maybe 100x what you're earning. Most of us are earning right here. Right? But if you want to find any one variable, let's say mean, variance, etc., what you do is you start taking samples and computing it. And those sample values will show a distribution like this. The reason in data science this matters is because if this were not true, center limit theorem were not true, we would never be able to trust the samples, isn't it? Right? And so what would happen is we would be forced to look at the whole population. Right? Though now you said mean is what about mean? What if I was looking at some other thing, right? Let's say min, max, or something like that. You would agree that if I take a sample min and sample max, they may not be the global min and global max of the population, isn't it? If you go to kindergarten and you look at the tallest child, that child is nowhere close to the tallest human being. Right? So there are two kinds of statistics. Things in which through center limit theorem, you can find the real value by taking lots of samples and taking the mean value of that statistic. The average itself falls in that category. Mean of mean tends to the global mean. But there are things, and median also sort of, but there are things for which it is not true. For example, we just looked at min and max, right? So, or even standard deviation. What happens is if you take children, let's say, you realize that if you look at school children, the spread of their height will be limited. much less than the spread of the population's height. Do we agree, guys? So you say that standard deviation is a biased statistic, means the samples do not give you a picture of the real, right? Am I making sense, guys? Do not give you a sense of the real. But mean is an unbiased statistic because the mean of the means would be tending towards the real mean. Whenever you look at data and you're trying to understand data, we understand data either through visualization or through some statistic, isn't it? You have to keep in mind that because we are looking at samples, not the population, am I really getting a true sense of the population or do I need to do some correction? Right? So many of you remember standard deviation. And this is one of the points that keeps coming up. What is the formula for standard deviation you're taught in school? X minus mu, right? Squared, sigma squared is equal to 1 over n. This is what we are told. Average of the square deviations. Yeah, this is it. But the implicit assumption here is actually that this is the n of the population. So the question is, most of the time we don't have access to the population, isn't it? We have access to samples of the data. So how do we go from a sample population whose standard deviation we can measure to and make some inference about the global population? If you know what is causing the skew, you can. So what happens is you will actually notice that most of machine learning AI happens with samples of data, isn't it? You never claim that you have access to all the data. So the right sample is a population square is what you do is it turns out that you put a corrective measure 1 over n. And that is why you notice that in most machine learning textbooks, you will see that the denominator has a -1. What does -1 do? It just slightly boosts it up. Whatever variance value you get for the sample, it just makes it a little bit bigger. Isn't it? It turns out that making it just a little bit bigger is just the right kind of adjustment you need to get a sense of the global population. Something to know about. Anyway, these are all parts of the field. So let me now take you to, oh, where exactly? That's a mystery. Do you have $1 million? No, no, I'm kidding. It is there. I mean, my TAs know it. Right? Even I have to find it out. So what I would like to do now is go to something called, well, gradient descent is an act of the machine learning. I won't go into that. I will go into something simple. I'll give you examples of, actually, I shouldn't look at it through this. I should through this here. Look at this data set, guys. So what is the journey we talked about? Exploratory data analysis, explore, visualize, if needed, clean, and then build a model. So we'll take a simple data set in which X is the factor, Y is the response. X is the input, Y is the response variable. And we will try to create a function, Y as a function of X. Are we together? Because Y is a number and X's input is a number. Since Y is a number, is it regression or classification? It's regression. It's regression. So what do? We look at the descriptive stats. It says this is the mean, median, etc., etc. We are going through the journey. We see, are there any missing value treatment that we need to do, impute values, etc. And many of the things I'm skipping because we have a very short course here. Data visualization, you look at this. Look at this image carefully. When you look at this image, what is it practically telling you? Visualizing this data, what is it telling you about the relationship between Y and X? It's a linear relationship. It's practically begging for a straight line to be drawn through the data. isn't it? So let us do that. We then what do we do? Let's build a model. These are different ways of doing it. We will you use for data science typically, unless your data sizes are huge, you can use scikit-learn. It's the most common library, or you can use neural networks, PyTorch, etc. Right? Uh, these are two popular libraries. So we will use something called linear regression. And what you're doing is you're splitting the data between the training set and the test set. Why do we want to do that? See, what you do is whenever you get data set, how do you know that the model is correct? And it hasn't just memorized it. It has generalized. What you do is you hide some part of the data randomly, take some part of the data, and you hide it under your pillow. Then you give it to the model, the other half, the other, not half, the other part, the training part of the data. You say you learn from this data. Now, if the machine has just memorized the data points as one extreme, then it won't be able to make predictions on the data that you have hidden, the X values that you have hidden, isn't it? It would go wrong. On the other hand, if it has really gotten generalized from the training data and come upon a good hypothesis, a good linear hypothesis in this case, then it should be able to make fairly good predictions on the test data that you have hidden. So keeping the test data hidden and testing the model after it has been trained on the training data, you get a realistic sense on whether the machine has memorized or whether it has learned something from the data, right? Whether it has built a valuable model from the data. Right? It is, just to give you a simple analogy, some lazy professors in my undergraduate in IIT, they used to give the same questions over and over again every year in the exam. So guess what people did? So in my college, IIT, it was practically a dhamma that if you can find a clever way to not study, you must. Right? So obviously, through the generations, a question bank used to propagate of the most important questions, 50 questions. And we knew that this prof is going to ask questions from that bank. So you thought, do you think that we ever studied that subject? Right? Nobody studied. We had far more important things to go, movies not to miss, cricket games to play, and other important things to do. Why would we study that subject? On the other hand, other profs, they would every year conjure up new problems. So we had no choice but to study those subjects. Right? So that is literally what happens with models in a realistic sense. Models run the risk of memorizing the data. The more complex, the more, just like the brighter the kid, the more they're looking for other ways of not learning, clever ways of not learning. It turns out over-parameterized models behave like somewhat like clever kids who will say, okay, I'll just memorize this first. And then you go through a process of overcoming that reality and saying, oh gosh, I really need to learn. Right? And they learn. So here we build a model. When you build a model, you need to find out how good the model is at making prediction. How would you know a regression model is good at making prediction? You would know by looking at the gap between prediction and reality. Right? On the data set that you had, test data set, you ask, the entrepreneur asks, how much ice cream, given this temperature on the beach, given this wind speed, precipitation, workday or not, factors, how much ice cream does this model say I would sell on the beach? And you happen to know what the right answer is. The gap between the two is the error, isn't it? Isn't it? The gap between the prediction and what actually happened, ground truth. What actually happened is often called in our field the ground truth in the test data. That tells you the error. Or in the training data, it tells you the error. Then somehow you need to create something called loss. See, in the case of an entrepreneur, loss is very tangible. Every day she is losing either money, either as lost revenue or lost unnecessary wastage of capital, isn't it? So, but what happens, let's try to quantify this. Look at this picture and tell me, this is one model. This too is a straight line, and this is a straight line. Between the blue and the yellow straight lines, which is a better model? And why do you believe so? Yeah. What it means is, for a given value of x, let's say x is this x, I'll take this input value, right? The predicted value, or sorry, the predicted value here, this y hat of x here versus the predicted value, this y, blue y hat of x, right? Why do you say that blue is much worse? Because the gap, the crucial gap here is much smaller than this gap between the ground truth and the blue prediction versus the ground truth and the yellow prediction, yellow model's prediction, isn't it? So this gap is y minus y of x minus y hat of x for any given model, isn't it? It's the error. But notice that errors can be positive or negative. But error is error, whether you overshot or you undershot. If you underestimated ice cream needed, you have lost revenue. If you overestimated how much ice cream would sell on the beach, you have lost capital, wasted capital, isn't it? But both are losses for you. They are both equally suboptimal situations. So you look at the magnitude of the error. What you want to do is, you want to focus not on the error itself, but the magnitude of the error. So there are two ways you can do that. You could, at one ways, you could just say, hey, I will just add up all the magnitudes to get the total error. Total error. That is common sense, isn't it? And I will gradually find a way to make a model, and that process is called gradient descent. But for today, we'll skip it. Tomorrow, we'll learn a little bit more about that. We need to add up all the absolute errors. When you do that, it is called some absolute error. But let's take the average error because you have lots of points. On average, how many errors you make in the data set? Mean absolute error. Mean absolute error. Mean absolute error will do. But observe that I could have done not just this, I could have done this to any power k. Isn't that true? I could have taken square, I could have taken cube. This too would have worked. I could have taken the square of errors, added them. That also makes sense. Right. Now there's something very interesting here. We want to, and Gauss discovered this is called the Gauss-Markov theorem. Gauss-Markov theorem. He says that k is equal to 2 under favorable conditions, certain conditions of, they're fancy words, homoscedasticity and blah, blah, blah. We'll forget about it. Let's use a intuitive word, under sensible conditions, right? K is equal to 2 is the best model. So quadratic errors, some squared errors. Square the errors and put it. There's an intuition that I'll give you why squaring is a good idea. See, when your model makes a depart just a little bit from the correct answer, it may be because of noise. No. Because instrumentation error may be involved. Do you agree? Okay. So you don't want to give that much importance to that. You want to give importance to pronounced departures from the ground truth. You want to give far more importance to big mistakes. An easy way to give far more importance to big mistakes is to square it, isn't it? Does that make sense? When you square it, you give far more importance to that. Or another very human analogy that I can give is, good parenting says that when the kids are doing little mischief, you shouldn't go shouting at them. You should just look at the other way around as though you didn't notice, right? But the moment they make big mistake, that makes it a teachable moment. You only notice and talk about mistakes that matter. It's somewhat like that. Quadratics are very useful. So that is mean squared error. This is the most common, k is equal to 2, right? So k is equal to 2, or any k you could take, but k is equal to 2 is the most common. Beyond that, you exaggerate the impact of large errors. There's a problem with mean squared error. The problem is the outliers, they can be outliers in data. So for example, you're measuring the temperature of patients, and suddenly there is a value that says 1000 degrees, right? Well, that's not plausible. Most patients are not made out of hot iron, right? So then you need to, then you don't want to be misled by data. The problem with raw usage in linear models of quadratic error is that it can skew the model unfairly. Right? People call it, even in nonlinear people. So anyway, I'll just mention one thing. People often believe that neural networks don't suffer from this. Linear, simpler models suffer from this. That neural networks, because they do something called representation learning, it's an advanced topic, don't suffer from this. Actually, they are wrong. This problem is still there. It's called the dominance effect. Yeah. Big departures still dominate. It has nothing to do with which model you use. It has to do with what formula you use to compute errors. It is still there. Anyway, so that is about regression. I hope we got a sense of regression. Or we are almost out of time today. So tomorrow we'll do a classification. We will do dimensionality reduction and clustering. But today I want to take you through more examples of regression. Let's look at this data set. Oh, look at this data. Is it a linear relationship? No, it's a non-linear relationship. It's sinusoidal, yes, very good. So now what can we do about this data? If you try to model it with a straight line, observe something interesting. You still get a mean squared error, that's reasonable. Coefficient of determination, R squared, there's something called R squared. It measures how explanatory is your model. How much better is it than a null hypothesis? Means there's no relationship between X and Y. Well, 53% looks respectable. Right? How would you know that your model is actually not a good model? And this is one of the things that people actually don't emphasize in the books. And I'm going to introduce you to. The topic is called residual analysis. See, it is the one thing that I invite you to never forget. Always do residual analysis in regression. Residual analysis is a measure of how much signal your model did not capture. It quantifies. See, there's something called, I'll use some big words. Can I use two big words? One big word is called epistemic uncertainty or epistemic error. And another big word is aleatoric uncertainty or aleatoric error. What are these big words? Epistemic means the model's failure to fully understand the ground truth or capture it, understand it. It is an epistemic thing, right? Epistemic means to understand. You didn't quite get it. So when you get a data that is sinusoidal and you try to build a straight line through this data, you realize that it's a failure of understanding the ground truth. Isn't it? Your hypothesis is simpler than the ground truth. Ground truth is not linear. It's more complex than that. Right? The opposite could also have been true. It is just two curves here. What if you made a model that is highly curved and had 6, 7 different bends to it? That also, now you have come up with the understanding of reality. You are hypothesizing that the real relationship between X and Y is far more complicated than the ground truth, isn't it? That is an error of what people call variance errors or overfitting errors or overcomplex. Like the complexity of your model exceeds the complexity of the ground truth, right? Whereas when you make a straight line through it at a certain angle, the best straight line still fails. The epistemic error that it's making is it has it is the complexity of your model is below the complexity of the ground truth, isn't it? It has bias errors. So what is your goal? The two ways. First is there should be a complexity match. But that's not the only source of epistemic errors. There are others. For example, suppose the relationship is not y is equal to y is proportional to x or some function of x, but what if it is log y is a function of x? It could be, right? So you need to take the log of y, or maybe y square is a function of, maybe y square is sine of x. Do you see that? Right? It could have been that, and that too comes under the field of epistemic errors. How would you detect that? The beautiful thing is residual analysis gives you a clue about that. Or it could be a fact that your model did not consider some variables that it should have. So for example, when you look at the uh, data and you notice that uh, that you see, okay, when you in the residuals, which is, what is the residual? Epsilon, the error bars, those are called residual. If in the residuals you see clusters, then, and I'm just mentioning it, then it's a sign that there is a categorical variable that you missed. For example, suppose you missed to account for the fact that it is a holiday versus a working day. It's a categorical variable, right? It's either one or the other. You know that sale is far higher on a holiday than on a working day, right? Those things will show up as clusters. Likewise, if you see seasonality you missed, right? Or temporal factor you missed, that also shows up in the residuals. So all of these things, they manifest themselves quite often. Not residual analysis doesn't capture everything, but it gives you a very strong sense of when you have your model is exhibiting epistemic errors, understanding errors. It is just another way of saying it is barking up the wrong tree, right? Or it is looking at it from the wrong perspective. That is what you say. Then what is the other? Aleatoric errors are irreducible errors. For example, instrumentation errors. There are certain things that can never be measured to arbitrary precision. Let's take an example. Can you measure temperature in this room to 20 decimal places or 40 decimal places? Is that possible? Instrumentation precision has limits, but actually, that is a very good point. Some things can measure. For example, if you measure distance with a scale, you can go up to millimeters. If you measure it with a vernier caliper, you go a little bit further. Right? If you measure it with millimeter equipment, you go further. So there is a precision of the equipment. Right? Beyond that, you have inherent measurement errors, but there are certain quantities which inherently cannot be measured to arbitrary accuracy. So for example, can human population, the average population of humans, be measured to 10 decimal places or 12 decimal places or 20 decimal places? You say, well, the average is of only 7.5 billion human beings. How can I go further? Right? Temperature is interesting. Temperature just means, higher temperature just means the molecules are buzzing around faster. Right? So the temperature is a macro state that is created by 10 to the power 23 molecules buzzing around with their kinetic energy, isn't it? There is a microstate, the velocity vectors of all the molecules, and there are massive Avogadro number of them bouncing around. Temperature is just the macro state of that. Therefore, it will never be measurable to arbitrary accuracy. Right? So those are realities. they all come under the aleatoric errors. Now, quite often, sometimes residual analysis gives you a clue to that also. Like, for example, if you forgot to take, when the model doesn't know something that it should know, then, in other words, your data did not have that, then the residual analysis does begin to give you clues to that also. Right? That is something to know, and that's a deeper part. So let's look at the residue. When you make a linear model, when you look at the residue, here is a basic rule, guys. A good model leaves no patterns in the residue. When you look at the residues here, are you seeing a pattern? Does your eye see a pattern? Clearly, it shows a pattern, right? I can see this pattern. That means your model is suffering from epistemic error. It is not formulating the ground truth correctly. Or there's a huge scope for improvement because a good model would not leave residue. So now let's try a better model. And this is the model. You can see this model straight line. It is the best straight line you can draw through the data, but it is not good enough. Let's make a polynomial regression then with bends. Now, a slightly better model, you're saying I'll go up to powers of cube, x and x cube. When you do that, look at your explanatory power, it has gone up. Look at the mean squared error, it would have gone down. Look at the mean squared error, 0.03. Is it much less than the mean squared error of 0.45? Much, much less, isn't it? And so you feel that it might be better. But again, guys, never trust statistic itself. If there's one lesson I want you to take out, either in understanding data or in looking at the models, people just say model metrics look good. Therefore, it's a good model. No, it doesn't say therefore it's a good model. Right? There are many slips between the cup and the lip. You need to look at many factors. So when you look at the residual, and the residual does not seem to have that much pattern, isn't it? No obvious pattern. Now you feel that yes, the model may be good. Right? Now, you look at this, and it does seem to be a reasonably good model. Would you agree, guys? We can look at another example. Data set 4. Let me see. Yeah, data set 4. What does data set 4 look like? Oh, like this. It should be easy for us to do polynomial regression. When you fit a good model to the data, when you fit a bad model to the data, in the residuals you see a pattern. When you fit a good, and then you can see this line is a hopeless depiction of the reality. On the other hand, when you fit a good model to the data, you see patterns like this in the residual, which is good, not a strong pattern. And would you agree that the model, the dark line, is pretty faithful to the data, isn't it? So that's a lesson to learn, guys, about this. Let's take something a little bit more complicated. Let's take the snaky data. I call it the snaky data because it seems to look like a snake. Right? So I created this. So see what happens. If you see a relationship like this, instantly your mind tells you that there's a complicated relationship going on, isn't it? And so you may try polynomial or complicated regression. And one of the things you will learn in the Foundations of AI course is that this is exactly one of those places where neural networks do very well. But okay. If you build a linear model, lots of patterns in the data, you would expect it to be a disaster. But it's not bad if you really think about it. See, what is a good enough model? This model is giving you a mean squared error of 197, R squared of 79. Fairly explanatory power. To the first approximation, this is workable to get started on day one. What do we call this? Minimum viable product. You have a minimal viable product. But let's do better. MVP. Then, suppose you did a polynomial model of degree 6. Now you get 96% R squared. Mean squared error has gone down from 176 to 38. Much better, isn't it? Let's look at the residual. There is pattern, but much less pattern, isn't it? But you notice that it has still left pattern lying around. You can still see that snaky behavior in the residuals. Do you see that? Gently, it's there. Means we are not yet on the best model yet, but still workable. You can literally call it your release 2, right? Version 2. So this is it. Now you might be tempted that let's overcomplicate the model. What you in model language, what you would say, let's over parameterize the model. Now here is something interesting. Certain models can be over parameterized and you don't suffer. Neural networks have that virtue. You can actually overcomplicate or make an over parameterized neural network. And they have something called a simplicity bias. They always try to simplify the understanding of real data. But not all models have that. Polynomial models don't have that. So what you will notice is that in the interior of the data, it does well. But in the peripheries, do you notice that this swinging up tail, it develops a tail. I call it the wagging tail phenomena, right? But it has a name. It is named after the great mathematician Runge. And the real name is Runge phenomena, which is, if you can't remember it, just remember it as the wagging tail phenomenon. Right? If you overcomplicate your model, then where the data is not dense, the model will be unsure. And the tendency of complicated models is to create a complicated picture of reality. Right? The inductive bias is towards complexity. Yeah, go ahead. Yes, for integration. The same range. Right? And when you look at it, do you see that when you look at it beyond the range of the data, how badly wrong it is? Right? That's one more thing to remember. Be careful about using your models to extrapolate. Right? You should know when you can and how dangerous it is. Interpolation is fine. Extrapolation is dangerous. Even when you interpolate, the regions where data is sparse, you have to know that simpler models, under parameterized models, have an inductive bias towards they will put a smoothing connection in between. Over parameterized models, their inductive bias is to insert complexity into that regions where the data is sparse. And at the peripheries, by definition, data is sparse. Your question. Better. This is it. Metrics and residuals. So what has happened today, these days, is if you look at the textbooks, almost all the textbooks will give you some metric. MSc is the most popular, but there are many metrics for regression. First thing is never trust only one. See, when you go to a physician, he doesn't just take your temperature and decide what's your problem, right? He looks at other things, looks at your heart, etc. So first, let's look at many metrics. They all are telling a story. Right? Yeah, no, not always. Not always. Um, Polynomials, yes, but generally neural networks are a little bit of a black box. They'll say, "Oh, we have a reality, but we cannot write it as an equation." It will do that. Polynomial regression. See, absolutely, you can write down the whole equation. It's very easy. They're polynomial coefficients. It will tell you what each of the coefficients is. And so what happens is you see these coefficients. So can you see it is this plus this times x plus this times x square plus this times x cube. You see that, right? So let me write it out for you. The model comes back polynomial. Let's say degree 3. It says that the parameters are alpha, beta, gamma, delta. These are 4 values it emitted in the model. So what does it mean? Your equation is yx is equal to alpha plus beta x plus gamma x square plus delta x cube. Literally. Right? This is your y hat. In 6 degrees, so then you have 6 terms. You can do that. Those are called piecewise models. And people do make piecewise models. So I'm just giving you a tippy tip of the regression world. It's a beautiful, vast, enchanted forest with many, many techniques and marvels in there and algorithms in there. Right? So coming back to it, you should always look at. So again, the point that I was making is, guys, know what does it mean to make a model complex? What does it mean to make a model simple? Under parameterize, over parameterize a model. Know the bias variance trade-offs people talk about. But actually, the new understanding is it's not a bias variance trade-off. It is about when can I expect bias, where can I expect variance errors, both. So there's more to this subject which we are not going into. But the point that I was making is don't just trust metrics. Don't just metrics are numbers, isn't it? Mean squared error is saying overall average error, isn't it? It is not telling you that in certain regions it's doing much better than in other regions, isn't it? It is not telling you in a very clear way what the explanatory part is. Do other things. Residual analysis has been sort of, for some reason, it has disappeared from most of the textbooks because people believe, especially in the modern age with neural networks, etc., they feel that no, 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 we don't need to do that. Actually, they're wrong. You should do that. It's one of the techniques that must be required because once again, the human eye instantly figures out if something is wrong. Right? What are we saying? That if your residual analysis plots show no pattern, it shows what is, there's a big fancy word. It's called homoscedasticity of the residuals. Then you feel warm and fuzzy that your model's epistemic understanding is good, right? It's gotten the hang of the data. On the other hand, if your model shows any kind of patterns, and some of these patterns can be very interesting. I'll show you one particular pattern that you can see. Anyway, this is a big topic. Uh, it's a little hard to condense what used to be a 3-month course into a 6-hour course. So I apologize for that. But I would like to show you something called power MNOP. Where is my power? It's here, somewhere here. Polynomial is here. Power transforms. Did I scroll past it? Power transforms. Here it is. So sometimes what happens is, see, look at this. What if you see this kind of a plot in your, so this is your data, right? This data also happens. It is, if you do an analysis of this data, in the residual, you see this, right? You see this very peculiar thing that the errors, they funnel out, right? And sometimes they bend, but they funnel out. I often jokingly call it the Sherlock Holmes pipe. It sort of looks like that, isn't it? Right? The technical word for that is, there has to be a big technical word for it, right? It is called heteroscedasticity. Right? So, how many of you remember the Mary Poppins word? So there's a story of a lady who is very good with kids. So the kids, she says that if you ever feel underconfident in the presence of grown-ups, you must just utter the word califragilisticexpialidocious, and they all memorize it and they feel very good about the big word. So I tell you that when you're learning data science and you're in a meeting and you want to really throw in your weight, then heteroscedasticity does the job. But have you looked at the heteroscedasticity? I'm joking, right? That's what you're looking at. That is a clear sign you're barking up the wrong way. When you see that in the residuals, generally doing polynomial regression, etc., will not solve it. You notice it's not solving it. What you're looking for is, you are looking for a power transform. Right? The relationship fundamentally is different. And the first power transform is attributed to two people, Box and Cox. And there's a very interesting story with which I'll end that. Apparently, Box and Cox were brother-in-laws. So Cox flew in from England. I believe Box used to live in Wisconsin. So the story, the way I heard it goes, it was winter. Apparently, they went out hunting. Trouble is, hunters are quiet, right? But mathematicians are never quiet. So they were getting bored because obviously they weren't able to hunt anything. And the best they could hunt was a good idea, which is that, what if we wrote a paper, and wouldn't it sound funny if the title of the paper was Box Cox? And so they came back and they started thinking, what should we write a paper on? And apparently it was the Box Cox transform. And of course, it's become a workhorse of the data science. I would like to call it the workhorse, but surprisingly, very few people actually know about it. But it's a very important transform you should do on your data. you should watch out for it. When you see this kind of a behavior in the residuals, your data is saying you're looking at it the wrong way. There's a power relationship between input and output. You need to do a power transform. Anyway, so today I'll end with regression. So today we did, what did we do? We did descriptive statistics, we did data visualization, and we did regression. Tomorrow we'll do classification, clustering, and dimensionality reduction. So I hope, folks, that it was interesting. It was some fun. And I notice the people on Zoom are uncharacteristically quiet. I don't know if they benefited. Oh, Irvin, nice to see you. Happy New Year to all of you, if I haven't said Happy New Year so far. Many familiar faces. Some of you I recall. Ram, nice to see you on Zoom. Ramki. Oh, oh, hey, nice to see you. Who else? All right, guys. So, any comments, any questions before I end today? That's a computer vision problem. It's actually very solvable. You do such things in the large language model course in the bootcamp. And believe it or not, it is not much coding. This field is all about understanding. See, did you notice that I barely wrote much code? And if you look at this here, you would be surprised. You see how small the code sections are? Both in hardware, in VLSI, and in software. People write reams and reams of code. One of the first things that it hits people is that the AI code, the data science code, is surprisingly condensed and short. So it's not about code. And by the way, nowadays, you don't write code. Your AI agent writes the code. You just tell it what you want and it does a pretty good job. Your job is simply to understand that code. Understanding 10 lines of code when you know the theory is far easier than understanding reams of code. Actually, I am scared of UI code. Anytime I see a pile of, like if I see a beautiful UI written in React, I say, what lovely. It's so intuitive, makes sense. And then I look at the React code and I run for the hills. Because I'm not good at it. But AI code is very short and easy. Very, very easy. It's an AI problem. And using vision language models, which we teach you, that problem is actually one of the, it will fall within the purview of bring your own project in the bootcamp and you can easily do it. Because we give you a similar problem, very similar problem. All right, guys, any other, let me see if there's a comment in the chat. Nice, guys. All right, so if there's nothing else, then we'll see you again tomorrow, same time.